Today we'll look at continuity and discontinuity. Most of the notes here today are not based on examples or anything like that. It's really trying to get you a conceptual understanding of continuity and discontinuity. So first we'll define it. So definition of continuity is at a point a function is continuous at x equals c if and only if so that's just some shorthand. These three conditions have to be true. So f of c exists. So in other words, the point has to exist. Second, the limit has to exist. And then third, it says the limit as x goes to c of f of x equals f of c. So the limit has to equal the point. So these must be equal. So those are the three conditions for continuity. Those three conditions you will have to know exactly in like that. So the point exists, the limit must equal the point value. Okay, next this statement. So when we're talking about some closed interval, that's when, well, that's what we're referring to here. So the function is continuous on an interval if and only if it is continuous for all x in the interval. At the endpoints of a closed interval, only the one-sided limits need to equal the function value. So we're going to talk more about that because that makes more sense in examples, but we'll do that a little bit later. Next, let's talk about types of discontinuities. So we're just going to put names to these discontinuities right now. So these would be two examples of a removable discontinuity. So in one of the assignments from last week, we looked at some piecewise functions that had these characteristics. So this would be a removable discontinuity again. And let's talk about why. We can see that the limit exists as we head towards x equals 3. This limit value would be 3. And it's removable in this way. So algebraically, we can remove it. Okay, so we have this function. We're going to take the limit as x goes to 3. So we can't plug in 3 exactly because we would get 0 over 0. So we have that indeterminate form. So this is what we're going to do. We're going to mess with that limit a little bit. If we look at the numerator, we could factor out an x, and we'd be left with x minus 3. And that's the same thing we have in the denominator, so we can cancel it. And then we have the limit as x goes to 3 of x. So this would equal 3, which is the same value we can see from the graph. So through algebraically canceling that, we can remove the discontinuity. And so that's the same case for what's presented in that second example. Okay, so next we're looking at different discontinuities. Let's pay more attention to the graphs so that this is more about language and describing what we're looking at. So a jump or step discontinuity looks like these two. So it looks like what it sounds like. So there's a gap. It jumps up or down to a different value. So this is this function here is called the step function. Because it looks like steps. We don't use that too often, but that's another one that would have a lot of these jump discontinuities. Okay, infinite discontinuities. These are vertical asymptotes. So in this first example, that would be an infinite discontinuity. The graph is not continuous across an asymptote. And the same thing goes for that second example. And so this is just another characteristic of a graph. It's not that the function is discontinuous, but it's another way to describe what we're looking at. So a cusp is a point on a function where the function is continuous, however, the derivative is discontinuous. And we'll talk about the derivative later, but that's what defines a cusp for us. So another way to look at this is it's a sharp point or abrupt change in direction. So if you look at this function below here, this function comes to a point at x equals 0, therefore that's a cusp. We'll see this a lot in piecewise functions. Here's another one. And one of the most common ones that we use is the absolute value function, which is a V shape, has a cusp at x equals 0. Okay, so for this example, this is based on the three conditions for continuity, where the point must exist, the limit must exist, and those two things must be equal. So we have a piecewise function, which we're going to have to look at in two pieces as far as the left and right hand limit. So piecewise function, we have a k in there, so that's kind of our issue with this one. So this letter A says find k such that h of x is continuous at x equals 2. So what this is saying, we're going to make this function continuous by finding a k value that makes them equal at x equals 2. So based on the three conditions at the outset we talked about, we'd have to find the limit. So it would be the limit as x goes to 2, and we have a piecewise function, so we have to take a left-hand limit and a right-hand limit. And we would use so the function h of x. And since we're coming from the negative side, we're going to use this top function, and we would have 2, or k, times 2 squared equals 4k. Then we take the limit from the right, and we're going to use this lower function, so it would be the absolute value of 2 minus 3 plus 4, and that's going to equal 5. So again, I'll write this in words. For h of x to be continuous, these limits must be equal. So we just take 4k and set it equal to 5 and solve for k. So k would be 5/4. So if we were to rewrite that function with k being 5/4, then the function would be continuous because the left and right hand limits are the same, so the limit exists. This function is defined at x equals 2. So that's based on those three conditions, so the function is continuous.